Good evening, everybody. Welcome to this distinguished lecture from Professor Eytan Modiano from Massachusetts Institute of Technology. Professor Modiano arrived last week for being part of a PhD grading committee here in KTH. And I just mentioned quickly some bibliographical notes, and in particular, Professor Modiano received his PhD in 1992 from University of Maryland, and is on the faculty at MIT since 1999. Please, you have 45 minutes.
Thank you. Good afternoon, everyone. So today I'm going to talk about optimal control of wireless networks, and my presentation is going to be two parts. I'm going to give some historical perspective. I'm going to talk about the particular optimal control framework that I'm considering, and this is a control framework that was started about 25 years ago, and I'll give the history of it and how it has evolved, and I'll explain the framework. And the second part will be some of our recent work in toward implementing this control framework. A little bit about myself and my research program. I've been at MIT since 1999, as Carlo had mentioned, and I've worked in 3 different areas, all of course to do with networks, network control, and network resource allocation, looking at space networks for quite some time, looking at terrestrial fiber optical networks using wavelength division multiplexing technology, and looking at wireless networks. The kind of problems that I tackle in all of these areas are very much the same. The problems of resource allocation and protocol design and optimization. Today I'm going to focus on the wireless work. And in particular, I'm going to talk about a cross-layer optimization framework, a well-known cross-layer optimization framework. And I will describe this framework, describe some of the classical results in that area. So the network that we consider is a wireless network where the communication links may well be time-varying communication links, subject to interference, mobility. We consider random traffic demand, so it is a stochastic network with stochastic traffic arrivals. And our objective is to develop network control strategies to maximize, say, network utility or network throughput in specific. And by control strategies, I'm referring to routing, scheduling, and flow control, and the kind of strategies that will dynamically adjust to changes in the traffic conditions, to changes in the network topology, and so on. And I will describe a particular framework, a cross-layer framework, that involves transport layer flow control functionality, network layer routing, as well as MAC layer scheduling. And the functions at each layer, as you will see in a moment, are coupled together through queue backlog information. And the objective is to maximize the stable throughput of the network, or perhaps maximize network utility. So here is the outline of my talk. I will spend about half of my talk in history. There I'll talk about the joint optimal routing and scheduling and flow control problems. And then the second half of my talk will be focusing on maybe recent efforts by us, my group, toward practical implementations of such. So the network model is adapted. It is, in fact, the model used by Leandros Tassiulas and Anthony Ephremides in their now famous 1992 paper on the control of wireless network. And so we consider a multi-hop wireless network with stochastic arrivals, where packets arrive into the network and are buffered in queues at the network, at different nodes in the network. The traffic ID, the statistics, are generally not known in advance. And they consider a time-slotted system, and they develop a jointly optimal scheduling and routing algorithm known as the backpressure framework. And the objective of the backpressure framework is to stabilize the network. In particular, the 92 paper of Ephremides and Tassiulas defines the stability region of the network to be the rate region, such that for any arrival rates within that rate region, the network can be stabilized, and outside the region cannot be stabilized by some control policy. And so by stabilized, just to be specific here, it is a stochastic notion where a network is considered stable if all of the queues are bounded and unstable otherwise, bounded in expectation. And as I said, in their paper, they developed a jointly optimal routing and scheduling algorithm that stabilizes the network for any arrival within this defined stability region. So again, the stability region is defined to be the region of arrival rates for which there exists some algorithm that will stabilize the network. And we can say that such an algorithm then is throughput optimal or achieves 100% throughput. So let me quickly go through the jointly optimal routing and scheduling algorithms by starting with scheduling. So in a wireless network, only a subset of the links can be activated simultaneously. For example, if we have primary interference constraints, then a node can transmit to a single neighbor at a time, and multiple links can be activated so long as they're not incident on the same node. So for example, these darker lines represent a possible set of links that can be activated simultaneously because none of these dark links is incident on the same node. That is called primary interference constraint. There are many such possible interference models. The paper is not at all specific as to what interference model to be applied. Another interference model could well be what is known as secondary or two-hop interference, where no two edges can be active if those two edges can be joined by a single other edge. So, for example, here, those two yellow or orange edges can be activated simultaneously because they are at least 2 hops apart. If they were only 1 hop apart, I would not have been able to activate them simultaneously. And then the throughput optimal scheduling algorithm is simple. It takes queue length into account, and it is called the max weight algorithm. In particular, what it does is it schedules the maximum weight activation set, i.e., you schedule the maximum weight set of links that can be activated simultaneously in each time slot, where the weight of a link is its associated queue backlog. So this is it. This is the optimal link activation scheme. You find the set of links that can be activated simultaneously that maximizes the sum of the queue lengths of on those links. So for instance, looking at this 2-hop interference example, suppose that the backlog on this link, on the links is as labeled. The 2 orange links have a total weight of 14. The 2 green links have a total weight of 12. The maximum weight activation would be the 14. And that's the set of links that you would activate. You activate those links, and then the weights are updated, and you activate the net set of links, and so on. And that is scheduling, and that is the optimal scheduling in the event that the traffic is only 1 hop. If the traffic is multi-hop traffic, then routing is also necessary, i.e., we have to find a path for the packets from the source to their destination. And the optimal routing algorithm, again proposed in that famous paper, is known as the backpressure routing or the differential backlog routing algorithm. And what backpressure does is it routes packets based on commodities. Okay, so a commodity, each commodity C corresponds to data associated with a given destination. All commodity 5 packets have to go to destination node 5. All commodity C packets go to destination node C. The routing algorithm is a hop by hop routing algorithm, and along a particular link, say link AB, we will choose which commodity to forward along that link at each time slot, and in particular, we will route the commodity C that maximizes the differential backlog along that link. Okay? What is the differential backlog along the link? It is the difference between the queue size of that commodity at the source of the link and the queue size of that same commodity at the destination. So for example, consider some commodity C, and the queue size at the source may be 3 for commodity C, the destination may be 2. The differential backlog is 3 minus 2, or 1. And now, what the routing algorithm does is for each link, compute the commodity that maximizes this differential backlog and schedules that commodity for transmission on this link. Okay, so what the algorithm does is it actually uses what we call backpressure. It routes traffic from nodes that have a lot of a particular commodity to nodes that have less of that commodity. Almost you can think of it as the way that water might flow in pipes, okay? From points of a lot of water to lower pressure. So it's backpressure. And this routing policy works in conjunction with the max weight activation that I mentioned in the previous slide. Namely, given these differential backlogs that are used for routing, the link activation applies the same max weight rule that I had in the previous slide, but now each link is associated with a new weight, where the weight of the link now is the backpressure of that link, the maximum differential backlog along that link. And this algorithm, the joint scheduling and algorithm, maximizes the network throughput. It is the throughput optimal algorithm. It will stabilize the network if any other algorithm could potentially stabilize the network. Okay, real quickly, pictorially, how does this work? Here is an example with one-hop interference constraints. You notice that you see the queue sizes and the respective commodities at each node. You can see that I labeled on each link the maximum differential backlog on that link. So for example, on this link, you can see that the maximum differential backlog on link 1 to 4 is with respect to commodity 6, and it's equal to 3, a difference of 3 packets. You compute the maximum differential backlog on each link. You compute the maximum weight activation, which is these 3 purple links, activate them, transfer those packets from the source to the destination of those links, and recompute the backpressure. You have new arrivals. You compute the new weights on each link, find a new next activation, and continue to forward packets in this way. And this is how backpressure works. That's the whole story. Okay? So that's the story. And this framework, designed 25 years ago, has actually found application in a lot of areas. First, already in the 90s, people applied max weight scheduling to input queued switches. Input queued switches are used at the heart of routers to transfer packets from input ports to output ports. And maximum weight scheduling is known to be the optimal input queued scheduling algorithm. In my first work on this topic, maybe more than 10 years ago, we applied maximum weight to scheduling in satellite and hybrid satellite terrestrial networks. We also, of course, extended it to power allocation in wireless networks in our work. And we also extended this framework to even reconfiguration of optical network topologies. So a lot of different applications. I'm really quickly going to explain a couple of our own works in this topic. Maybe the first time I worked on this was over 10 years ago now. And we looked at the problem. I was working on scheduling in multi-beam satellites. And the problem with multi-beam satellites is a geosynchronous, for example, satellite may have hundreds of terrestrial beams. Each beam maybe has a diameter of about 80 kilometers. And associated with each beam is a different, let's say, transmitter, if you will, or transmitter system on board the satellite. And in practice, the transmitters on the satellite can only activate a few beams at the time, not all of them simultaneously. And the question is, how do we activate those beams? And how do we allocate power to those beams in the way that maximizes the network throughput? And in fact, we found that this was a very natural application of the max weight framework. And the optimal beam scheduling and power allocation scheme was simply a generalization of the very same max weight rule to power allocation over the satellite channel. In particular, the optimal power allocation vector is given by this maximization. You optimize the product of the queue length and the rate of the particular transmitter and beam as a function of the power allocated to that beam and the channel conditions on that beam, subject to a total power constraint on the satellite. So you solve this simple optimization at every iteration, and you get the optimal power allocation to the different beams. You get different rates on the beams, and then you continue to solve this problem. And we've actually applied this framework to military satellite systems in the United States. The framework that we described earlier was looking at discrete activations, where we can activate subsets of links. More generally, you can think of applying that framework to wireless networks with power allocation, where we have actually time-varying channel conditions. So the channel conditions are not static, but can be varying in time. And the rate associated with each link in the network is a function of the time-varying channel conditions, as well as the power allocated to that link. And this can be used to model things like interference between the links. And the interference, of course, is going to be a function of the power that I allocate to the link, as well as the channel conditions and so on. And again, maybe a decade ago, we generalized the max weight and routing and scheduling framework to this kind of power allocation. For example, the rate on each link might be modeled, just for example, of course, as given by the Shannon capacity formula for additive white Gaussian noise with interference. And then we are able to show again that the max weight framework, it's still the very same back pressure, but now the rate on each link is again a function of the power allocation to not only that link, but to other links, and it can be modeling interference as well as time-varying channel conditions. So again, it's a generalization of the back pressure framework to optimal power allocation. So that's still history. This framework, very naturally a wireless framework, but can also be applied, just like we mentioned before about input queued switches, can also be applied to optical WDM networks. So the way networks are built today, if you think about the terrestrial wired networks, is that we have an optical transport network using wavelength division multiplexing technology, where these optical light paths are used to connect electronic routers, say IP routers. And the connectivity between the IP routers can take on different topologies depending on the way that I choose to route the optical light paths on the fiber. So I can actually dynamically change the way I connect these different IP routers by changing the light path configuration between the routers. And so the optical capacity is huge. The electronic processing capacity of routers is a lot more limited, and it's advantageous to reconfigure the connection of the routers, the way I connect them, in order to match the traffic conditions, so that I have to do less multi-hop routing, and so that I can need less electronic processing of the data. And in fact, in this context, what we developed are optimal algorithms for reconfiguring the connectivity between the routers based on traffic conditions. And again, this particular configuration was an application of back pressure routing and max weight scheduling to the optical domain. So lots of different applications for this. OK, so you see, the max weight framework that I described so far involves routing and scheduling, and is optimal in the sense that as long as the arrival rate to the network is within the stability region of the network, then it will stabilize. OK, but in practice, I don't know the stability region of the network. And it's very possible that the arrival rates are outside the stability region of the network. And the question is, what happens when the arrivals are outside the stability region? I said nothing about that, and neither did Leandros Tassiulas back in his 92 paper. And in fact, an interesting thing happens. When the arrival rates are outside the stability region of the network, there's no guarantee about what max weight might do. It might do something totally stupid. It will actually take the arrival rates, and it will map it to something on the boundary of the stability region, but the point of operation may not at all be what we want. The point of it is, when the arrival rates are outside the stability region, some packets have to be kept out of the network. Some packets have to be dropped, if you would, in order to bring the arrival process to the stability region, or else we cannot stabilize. But the question is, how do we do it optimally, and how do we get the optimal operating point on the stability region? And this really becomes a natural network utility maximization problem. We can formulate an optimal flow control problem as a network utility maximization problem, whereby if I let Ri be the rate that I allocate to, say, session I in the network in steady state, and I have a utility function, G of R, be the utility of allocating rate R to, say, session I, then the optimal flow control objective or the optimal utility maximization objective can be simply to maximize the sum of the G of R's over all sessions, subject to the allocation rate to be within the network stability region, and of course, to be less than whatever arrival rates I have. And such network utility optimization is well known and can be used to model a wide range of quality of service or fairness objectives. Moreover, if I know the arrival rates to the network, and I know the network topology, and I know the channel statistics, i.e. if I can really know the network capacity, then presumably I can actually solve such network utility optimization using standard optimization techniques and obtain the optimal rate allocation. That I can probably do. In fact, we know how to do that kind of thing. The problem is that in practice, we don't know the capacity region of the network. We don't know the arrivals. We don't know the traffic, the changings in the wireless channel. And we want to have a dynamic control strategy. So in fact, quite a while ago, we actually developed such a dynamic flow control strategy. And it's an optimal strategy that works jointly with backpressure and max weight. And in particular, our strategy works as follows. All packets that arrive into the network first enter what I call an overflow buffer or reservoir. And then there is a control valve between the reservoir and the network, whereby the control valve decides how many packets, that's the rate RIC there, to admit into the network from the reservoir at any point in time. Okay? So the valve controls how many packets to admit in each time slots. And what I will show is, in fact, the optimal rate that I admit into the network at any time slot is based entirely on the queue length at the entrance to the network. Once the data is inside the network, we show that the optimal routing and scheduling inside the network is still max weight and backpressure. And we show that our algorithm, which I'll detail in the next slide or two, comes arbitrarily close to the optimal operating point. In other words, it's optimal. So here's the algorithm. It's super simple. At any time slot, the optimal flow control picks the rate to allow into the network at every node I with respect to commodity C, that's RIC. That is the solution to this optimization. You maximize the sum over all commodities of G, which is the utility function of the rate R, minus the product of the rate R and the queue length UI at the ingress node, at the entrance to the network. So what you see here is the optimal rate that I allow into the network for each commodity at any point in time depends on the amount of data in the buffer. So if there is a lot of data in the buffer, you can see that from this equation, I will let less rate in. If there is little data in the buffer, I will let a higher rate in as well. There is a constant V. I'll say more about the constant V in a second. It's just a control parameter that allows me to optimize performance. And we can show that this algorithm, by choice of V, can become arbitrarily close to the optimal operation of the network. So it's a dynamic, decentralized algorithm. It doesn't require, actually, any knowledge about the network. It really works at the ingress only. So it's kind of super easy to implement, although I will say some things about implementation in the second half of this talk. So just for example about this algorithm, how simple it is. If I have linear utility functions, which it can be used to model, say, optimizing throughput, then the control becomes very, very simple on-off control. If the queue length at the ingress is less than some threshold V, then I let the maximum rate in. If it's greater than V, I don't let any traffic in. If I wanted to model proportional fairness using, say, logarithmic utility functions, G of R is log 1 plus R, then the rate that I let in at every time slot is inversely proportional to the queue length. Nice. Very simple to implement. I will show more about implementation in a second. I'm going to hurry through the next two slides in the interest of time because I think Carlo mentioned I have 45 minutes. Is that correct, Carlo? 45? So I need to hurry up. Bottom line is the algorithm can be shown to come to arbitrarily close to the optimal operating point. If you define the optimal solution to the utility maximization problem that I had mentioned earlier, we can show that the algorithm comes arbitrarily close to this optimal utility. In fact, we get closer and closer to optimal utility by increasing this parameter v that I had mentioned earlier. At the same time, though, as I increase the parameter v, I will get greater and greater delays. I won't go into the detail of this simulation, but it shows you that there was an optimal operating point that we computed offline, and then we show in simulation how the achievable throughput slowly approaches this optimal point as I increase v, but we also show how the delay increases as we increase v as well. Not exactly shocking that in networks, as you increase throughput and you get closer and closer to operating the boundary of the stability region, you'll get increases in delays. So that's the history perspective. This is all work from 25 years ago to 10 years ago or so. And that's a nice theoretical framework. In terms of practical implementation, there has been some work, but by and large, this cross-layer framework, which is known for its elegance and optimality properties, has really been only a theoretical framework. And in the last 5 years, it's been my goal to try to move this theory to practice and to try to develop practical protocol implementations, to try to think about algorithms that are designed with practical considerations in mind, rather than just keeping this as a theoretical framework. And I will now describe our approach and some of the efforts we've made toward this end. We're still doing these kind of things. My group is still very much a theory-oriented group. We don't build things. So what we're trying to do is we're trying to develop algorithms that are still theoretical, but take practical considerations in mind. I will show you a mix of this today. I'll first talk about something very pedestrian. I'll talk about implementing this very framework I just mentioned using UDP and 802.11. And that will be all simulation-based. And then I will describe a couple of efforts in recent years about actually developing algorithms that are theoretically robust, but yet take practical considerations into account. First thing first, we wanted to implement this flow control scheme using UDP and 802.11 because that's something that every computer uses these days. And I had a postdoc. All of this work actually is my former postdoc, Julia Sefaroglu, who is now a professor at University of Illinois, Chicago. And the first thing she wanted to do is try to implementing things using UDP, because UDP allows you to actually control the rate that you allocate to the sources into the network. The thing about the max weight framework and the flow control scheme that I just showed you is that we need per flow queues at the source node, because the queues at the source node, if you recall, were per commodity or per flow, if you would. The problem is that if you look at implementations, whether it's your laptop or what have you, they tend to have just one queue per node. Basically, it's one queue per radio interface, per line card. So the approach that we take, and it's not an unusual approach, is to implement per flow queues at the network layer as opposed to at the link layer. So the kind of approach we take is you implement network layer queues. You have network layer queues, and you solve the optimization problem at every time slot at the application layer. And then you use UDP to send those packets, a solution to the optimization, to the network layer queues. I'll show more about that in the next few slides. And then the network layer queues will feed the packets directly to the wireless interface. But there are some issues there, especially when it comes to 802.11. The problem with 802.11 is that, in fact, not only I can make these fake network layer queues, no problem, but the 802.11 card still has a buffer at the link layer that I need to contend with. And if that buffer is buffering packets in there, then it's very hard for me to control which packets are going on the link layer queues. The approach that we took to solving this problem, just as a practical approach, this is not a theoretical framework, is to develop a distributed yet localized implementation of max weight scheduling on top of CSMA-CA. So what we did is we actually collected 2-hop queue length information from the local neighborhood, Each node collected this local queue length information from his neighbors and fed that queue length information at the network layer into an implementation of the max weight algorithm. The maximum weight algorithm is implemented by each node individually, and those nodes individually will decide whether indeed it is their turn to transmit, i.e. do they have the maximum weight within the local neighborhood. Then they will calculate the commodity that has the biggest backlog and send those packets to the link layer. So each node will make his own decision based on local queue length information. Another way to look at it is this. So we have the transport layer flow control, where in fact we solved the optimization problem that I showed you in the previous slides. The network layer flow controller decides how many packets of each commodity to transmit to the network layer queues. These are the network layer per commodity queues. The network layer will then compute a max weight algorithm using local neighborhood information. So you get queue size information from all of the 2-hop neighbors, compute the max weight algorithm, decide when it is your turn to transmit, decide which commodity to send, take that commodity and send it into the link layer buffer. And when you do it that way, you make sure that the link layer buffer is always empty, unless when you have a packet to send, it only has that one packet. So that is sort of a kludgy but effective way to make sure that there's nothing in the link layer buffer but the packet that you want to send. So this is basically the algorithm. I won't go into the detail of the particular simulation using NS, but what we did is we tried to simulate the performance of this algorithm using different utility functions, both linear and logarithmic utility functions, comparing performance to just plain UDP and FIFO scheduling to our algorithm. Not surprisingly, what we found is that, in fact, our algorithm does pretty much the right thing. For example, this is just a downlink setting, just a simple downlink setting. And if you just did UDP and you have two commodities, what I show here is that UDP allocated half the rate to each of the two commodities. But when I had linear utilities and I gave slightly greater weight to commodity 2, what I found is that our algorithm was able to allocate all of the traffic, all of the rate, to the higher priority commodity. This makes perfect sense. That would be the solution to the optimization problem that you want, because you get higher utility there. When I use logarithmic utility, I was actually able to achieve the proportional fair rate allocation. So I don't go into too much detail there, but I'm basically saying it works. What happened here? Good. So that was sort of trying, what I described so far is a kludgy approach to making max weight, back pressure, and all of that work together with existing, say, 802.11 max. But my goal really is to try to look at this optimization problem from a practical perspective and resolve the optimization problem taking into account practical constraints. Let me give you an example of what I mean by that. Back pressure routing is a network layer functionality. Okay, so excuse me, routing is a network layer functionality. Back pressure routing, on the other hand, involves joint routing and scheduling. So routing is network layer, scheduling is link layer. Where would I implement back pressure? Do I implement it at the network layer, as I did in the previous slide, or do I implement it at the link layer? Well, each case has its own problems. If I implement things at the network layer, as I did in the previous slide, then it requires a lot of synchronization between the network layer and the link layer. It's a bit complex and maybe even kludgy. At the link layer is almost impossible because of limited memory and functionality at most link layers, and the fact that I only typically have one queue per link layer. So we said, OK, let's try to rethink back pressure entirely and consider a situation where indeed I have separate routing and scheduling rather than joint, so that I can do routing entirely at the network layer, scheduling entirely at the link layer. So we wanted to look at it this way. We said, OK, suppose that, as it is in practice, I have network layer per flow queues, but I also have one link layer queue per link, as opposed to multiple queues per link. And this allows me to separate the network layer and the link layer queues. So if what I described so far and back pressure requires at each node I, one queue for each commodity, now I'm going to do more than that. I'm going to require at each node I, 1 queue per commodity, and I'm going to also require at each node I, 1 queue per link, exactly 1 queue per link plus 1 queue per commodity at the network layer. So network layer queues per commodity, link layer queues 1 per link. And then I want to resolve this optimization problem assuming this queue structure, because this is a realistic queue structure. So you can formulate this problem as basically, again, a network utility maximization problem, but here now we'll have flow constraints for routing traffic from network layer queues to the various links, because that's really the routing function. The routing function is taking packets from the network layer queue to the link layer queues. So when you reformulate this problem, you can again solve it using duality, and the problem decomposes very nicely into 3 subproblems again: a flow control subproblem, a routing subproblem, and a scheduling. Okay? And if you look at it, the flow control, I know it's not familiar to you, works out to be exactly the same as the flow controller that I showed you about 5 minutes ago. Namely, the optimal flow control is allocating the rate, which maximizes the utility minus the queue size times that rate, something like this. The routing works out to be backpressure, but not quite the same as backpressure. It is still, the optimal routing turns out to be to route the commodity on link ij that maximizes the queue size at the source minus the queue size at the destination of that link. That is still the standard backpressure, minus the link layer queue. That's what's new here. So it's not exactly backpressure. You also have to take into account those packets at the link layer on that particular link. And the scheduling now is exactly the same as max wait, but now I'm only using the link layer queues, not the network layer queues for scheduling. So indeed, we're able to completely separate routing from scheduling. Routing is backpressure-like, using just the backpressure, but taking into account those packets in flight, those packets in the link layer queue. Scheduling is max wait-like, but not using the network layer queues per commodity, but rather just the link layer queues that we reestablished. Is this throughput optimal? We think so. We don't have a stochastic proof. We do have, it does solve the network utility optimization problem. We do not have a stochastic proof of stability, but we think it is from simulation results that we've shown. We've simulated it along various topologies and conditions, and we always find that it does exactly the same as traditional backpressure. We even implemented it using Android devices. I'm going to skip the implementation detail and hope that you trust me that it kind of works. Yeah. And I'll move on to another problem with max wait. I'm not stopping for questions because I know we're being videotaped, and I'll take questions at the very end of my presentation. So I'm getting close to the end of the presentation. Another interesting problem. People have observed, and we have observed, that in fact, when you try to use backpressure routing and max wait scheduling in conjunction with, say, TCP, the two don't work together. Why don't they work together? Because, interestingly, TCP has a window flow control scheme, and the way TCP window flow control scheme works is that you have a window size of packets you get to send into the network, and you can advance your window or increase your window as you get acknowledgements. So TCP tends to favor flows that are responsive. If you get quick feedback, you'll be able to send more packets into the network. Max wait works in a different way. Max wait scheduling will prioritize those flows that have a large queue. Flows that have a large queue are basically flows that did not receive a lot of the resources, that have not been scheduled in a while. So in fact, these two have very differing objectives, and they don't interact very well together. Take a look. Consider these two flows at a single node. One has 3 packets in the buffer, the other has 1 packet in the buffer. Max wait scheduling naturally will schedule the flow with the 3 packets in the buffer. That flow will get a packet through. That will generate an acknowledgement. When the acknowledgement is received at the source, TCP source, it will send more packets into the network. As it sends more packets into the networks, that flow still remains the larger queue at the source and gets served again and again. So you generate acknowledgements. This guy doesn't get to be served, doesn't generate acknowledgements. This guy's TCP session keeps sending more packets into the network and continues to have a larger queue. You can simulate this setting in 2 flows over this simple example, and you'll see exactly what I'm talking about. The flow that gets a head start, the flow that gets to transmit these packets first, gets to send more packets into the buffer, gets to have the bigger queue, and gets to continue to dominate the system, and gets 100% of the throughput. The other flow is killed. How do you, so this is a fact. I mean, you can simulate backpressure with TCP, and you'll see this in many, many settings. So how can you fix something like this? Well, perhaps you can redesign backpressure, or you can redesign TCP. You can go and ask to redesign TCP. That won't happen. Maybe you can go and try to replace backpressure a bit. And what we did here is a bit of a hack. Not entirely so, though, is we developed a version of backpressure that is, we call it TCP-aware. I don't think it's TCP-aware, but it's at least cognizant of the fact that you don't want to starve any flow. So the backpressure is changed so that instead of just having the weight be the traditional backpressure, we make it be at least K. So we have a maximization where the weight of a given commodity is at least K. So the source queue is set to be at least K for every commodity, which means that every commodity will get some chance to transmit. And it's easy to show that this kind of this kind of change in the weights maintains the optimality of the throughput optimality of backpressure. It also maintains fairness by proper choice of K, and it interacts very well with TCP, both when TCP flows are all adjusted this way and not. And we see that for the simple example I gave in the previous slide, indeed, the 2 flows get a fair share of the bandwidth. And we simulated it over wireless networks, and we showed that the flows get a good share, an equal share of the bandwidth, and also improve throughput performance as compared to other routing schemes. So that's TCP. And then the last thing I want to talk about, and it's actually an area that I'm actively working in right now and I'm quite excited about, and it's backpressure overlays. So if you think about the backpressure framework I just described, it requires a homogeneous network. It really requires every node in the network to be able to implement backpressure, every node in the network to be able to implement max weight. So if you think about adaptability, if you think about introducing this technology into a system, it's not that practical. Suddenly everybody has to have this completely different mechanism of routing and scheduling. It doesn't make a lot of sense. So lately I've been interested in this idea of how do I implement optimal control, or how do I design optimal control algorithms that are compatible with existing technologies so that they can be adapted without requiring every node in the network to adapt a new technology simultaneously. Okay? And this is one example. And the example here is the idea of backpressure overlay. Suppose that instead of having every node in the network be able to do backpressure routing, I only allowed or only required a subset of the nodes in the network to do backpressure routing, and let the rest of the nodes do the traditional legacy routing, say shortest path routing. So that would require me to only upgrade a small subset of the nodes. And the question is, so we developed this overlay architecture for backpressure, where, as I show in blue here, only some of the nodes do backpressure, the rest just do legacy routing. And so the overlay nodes are the controllable nodes that are capable of doing whatever I want, bifurcate the traffic as backpressure does by sending data in multiple directions to the destination. But the non-overlay nodes are legacy nodes. They're old technology. They're not controllable. They will do whatever they know how to do, which is, say, shortest path routing. And our objective in this setting is to maximize network throughput by proper choice of where to put these overlay nodes, to find the optimal place for overlay nodes, and to find, say, the minimum number of overlay nodes I need to achieve maximum network throughput without having every node in the network be an overlay node. And finally, to develop routing policies to implement the overlay nodes that will work effectively with this underlay and still achieve 100% throughput. So that's an area we started a couple of years ago. You can see in this picture that if every node, this is a cartoon, if every node was an overlay node and could do backpressure routing, that will achieve the maximum capacity region of the network. If every node was confined to be a legacy node using shortest path routing, that will define the shortest path routing capacity region of the network, and it will be much smaller, presumably, than the full region that allows me to do full backpressure routing. If only a subset of the nodes is allowed to do backpressure routing in overlay nodes, then presumably I will only achieve a subset of the full stability region. But the question is, can I achieve the full stability region with only a subset of the nodes? The answer is yes. The answer turns out that simple result that says that if I choose my subset of nodes that are capable of doing backpressure routing in such a way that all of the possible paths in the network can be exploited, then it is possible to achieve the full stability region of the network. So here's the idea. Non-overlay nodes are confined to, say, using shortest paths only, just shortest paths. So if you look, for example, at this network, simple topology, and I want to look at traffic going from the source to the destination, if I just do shortest path routing, as non-overlay nodes would do, I only have one path available for me. That's it. But you can see that there is another path that could increase my capacity substantially. Problem is, this path will not be arrived at with pure shortest path routing. If you're sending packets from S to D using legacy technology with shortest path routing, this is it. That's all I got. Now, I want to exploit this path. I'm going to put an overlay node here. Now, backpressure routing implemented at overlay nodes can send packets either directly along the shortest path or can send packets on the overlay network from S to O and then from O to D. That would work because S to O is the shortest path going this way, and then there's a shortest path from O to D this way, and I get both paths. I get to take advantage of both paths. Again, if I didn't have this guy here, I would never use this path to go from S to D. I could never use this path to go from S to D, not using legacy routing. But if I'm implementing some kind of backpressure over these overlay nodes, those three, then I can use this path or this path. Okay? So the point is, you've got to be able to put enough overlay nodes out there to exploit the full richness of the topology. In this example, and in general in any ring type of topology, all I need is 3 overlay nodes to be able to exploit fully the ring structure. In more complicated graphs, you need more overlay nodes. Won't go into the details here. I'll just tell you that we developed algorithms that minimize the number of overlay nodes needed to achieve the full capacity region and create all of the paths in the network. Well, we find through experimentation, really, on random graphs, that something on the order of 8% of the nodes is sufficient to achieve full capacity. So I only need to upgrade fewer than 10% of my nodes, 8% of my nodes, to be able to exploit all of the paths in the graph. The next challenge is a very interesting one. So I have this overlay network, as I show here. And now I want to use a routing strategy in this overlay network to fully achieve the stability region of the network. Something interesting happens here. Using pure backpressure now over the overlay is no longer optimal. I won't go into the detail. I'm out of time. But we developed an algorithm that in some circumstances is optimal. And it does backpressure, but a little bit differently. It computes between overlay nodes the traditional backpressure, namely the queue size at the source minus the queue size at the destination. But it also takes into account the packets in flight. So in fact, the backpressure is defined to be the queue size at the source minus the queue size at the destination minus those packets of that commodity in flight along that path. And then it does the routing based on this backpressure. And it's not optimal. I can show counterexamples where it's not optimal. But in certain settings, it's actually, we can show that it's optimal as well. And this is a problem we're still working on. What is the optimal routing in overlay networks? So you have an overlay network that is allowed to do any routing scheme you want. You have an underlay network that is doing something like shortest path routing. What is the optimal strategy in the overlay is the problem that we've been tackling. And we have a submission on that to TON. So that's it. I'm done here. My research agenda lately has been in this area of network control to really look at some practical aspects of control algorithms and develop new control algorithms that take practical constraints, such as the fact that I need to have routers both at the link and at the network layer, not only at the network layer, take practical constraints into account in designing such algorithms, not as an afterthought, but in advance. And I'll stop here and take questions.
You have time for questions.
So I really like your idea of kind of looking at which nodes do I really need to achieve the full throughput vision. So in the example though you gave with the two links, it was clear that there were just two paths relevant. One of the middle nodes, for example, the top path that could be. Does the idea just need these intersections, or can we do even fewer nodes than this? That's not clear to me. So
It's beautiful, yeah. You got it. I mean, okay, so
Eytan,
I'm sorry. So the question is about this. So I talked in the last, in the very last slide about this idea of placing of overlay nodes and what is the optimal placement of overlay nodes. Intuitively, the answer is, and the question is, okay, in the case of a ring that I just showed there, it's obvious that I just needed one more overlay node to achieve both paths, correct. In general, it seems intuitive, and I think your observation is correct, that you need to put overlay nodes at intersections. Whenever there's a need to bifurcate traffic, that is when I need to put overlay nodes. That's a reasonably good intuition. Not sufficient, and not even necessary. There may be some intersections that I don't need to place overlay nodes in, and there may be other opportunities, because if you can think of a graph that consists of multiple rings that are interconnected, you can see that there may be places where I need to put overlay nodes that are not necessarily intersection nodes. We do have a paper on that. It was MobiHack 2014, and it goes into all the details of what are the optimal structures. And I think there was another question, same area. Yeah?
Thank you for the talk.
Thank you.
I have actually two questions. The first one regarding the implementation. We know that there's a, you have to compute this optimal problem every cycle, every time you want to transmit. How does that scale, especially for larger networks? And with the software-defined networks, which probably touches to the last section that you mentioned about overlays, would that solve the problem?
Yeah, great question. So the question is this. I described everything as an optimization that needs to take place on every time slot. And if you're going to implement something like this on a time slot by time slot basis in a network-wide setting, that's obvious, not realistic. So how does it scale? How does it work? So there are two answers to this question. The simple answer and the true answer is that, in fact, these kind of algorithms have been shown to be throughput optimal even when they're not implemented on a slot-by-slot basis, but say on a epoch-by-epoch basis. So choose an appropriate time scale for your implementation. Say I want to recalculate the optimal backlogs or the backpressure every 100 milliseconds and operate on that time scale, and the algorithm will work. There are multiple facets to your question. I'm going to try to say a few more comments here. So one answer, don't do it on every slot basis. Makes no sense. Do it every epoch of whatever number of milliseconds you're happy with. Not enough, too, because that still requires in a large network to suddenly compute a centralized optimization problem. How can you suddenly compute the centralized optimization problem in a large network? Is that realistic? Nobody thinks it's realistic. So one of the things that people have done, including us, but I chose not to talk about it, was distributed implementations. I chose not to talk about it because if I did that, that would have been more history, and I wanted to move on to something new. About 5 years ago, a whole community of people worked on distributed implementation of max weight algorithms, and a number of such algorithms that are based on local decisions, greedy local decisions that are shown to perform very well. So that's a second question. And the third possible thing, perhaps you're right, that even our overlay approach may simplify and make the solution more scalable as well. No, I'm nodding in agreement, actually. I don't know why I shook my hand the wrong way. Absolutely. The answer is yes and no. I'm nodding in agreement in the sense that the question is great. This is clearly the important direction. It's even more important than you realize because you have to understand that backpressure routing has a terrible property of routing packets in loops unnecessarily. So it can be very delay insensitive. So we need to improve upon that. There are efforts to try to make max weight be more delay sensitive. To that, the answer is largely yes. For example, we've developed a loop-free version of backpressure, which is nice, right? So now you don't have to worry about the looping. But what you're asking is more than that. Can I have a delay-sensitive version of it? Can I have an algorithm based on, say, backpressure that actually optimizes delay? The answer to that is no. Optimizing delay is, let's just say for simplicity, impossible. But maybe you can have variants that perform well in terms of delay. That's possible. And I think that's actually an active area of research.
Other questions? I have just a curiosity that is related to the last question here, and is that now in the study so far, one actually can still look at the delays in the sense that okay, let's implement a certain algorithm and that maximizes the throughput, and they look what is the delay that is achieved. But again, wouldn't it be sometimes meaningful to try to define regions of minimum delays? So I don't know, something like that. You have a region for the maximum capacity, then one could define also the minimum delay that is achievable, and then later one could ask if there are algorithms that tend to that minimum delay.
So two things. First of all, we're talking about stochastic networks. So to speak of minimum delay in a stochastic network is probably not as easily defined. It wouldn't be a scalar or even a vector. Having said that, the question is more, would it be worthwhile to try to characterize algorithms that are delay optimal? And it turns out that in most settings, delay optimal results are very hard to achieve, except for the very simplest of network topologies. So yes, there are efforts toward that end, but if you think about it, at the minimum, you'd say, well, I mean, you should be able to write a dynamic program that will minimize delay. But then the solutions are not appealing. So if you want to get a practical solution that's delay optimal, well, then it tends to work only in the most minimalist of settings, in a very, very simple setting. So the answer is generally it's been difficult, but not impossible, but difficult.
I think if there are no more questions, then thank you once again. Thank you.
Thank you.